So we saw Laplace transform. We saw that basically we obtain Laplace transform as nothing but an extension of Fourier transform. We multiply the given time domain signal with a decaying exponential and compute the Fourier transform, which we refer to as Laplace transform. The inverse is also obtained in a similar fashion. And we said that Laplace transform is completely defined not only by the expression x of s, but also with the region of convergence. Now there is something more that we can do with the Laplace transform when it is rational. So what do we mean by rational Laplace transform? So we saw an example earlier. If x of t was e power minus at u of t, then the corresponding Laplace transform looked like 1 by s plus a. Correct. So this is what we refer to as a rational Laplace transform, meaning you can express that as a numerator divided by a denominator polynomial. So there is a polynomial here. So n of s is nothing but some polynomial. So let us say some bm times s power m. M goes from 0 to some capital M, and d of s is the denominator polynomial where some n goes from 0 to some capital N, c n s power n. So these are two polynomials. So if you can express the Laplace transform as some b0 plus b1 s plus b2 s square up until some bm s power m divided by c0 plus c1 s plus c2 s square up until some cn s power n, then such a Laplace transform is referred to as a rational. So do you remember where do you see such forms? If you remember in the Fourier transform examples and the problems that we solved, any RLC circuit ends up having a Fourier transform which look like this. Whenever you have differentiators and integrators, eventually the system equation could be expressed in terms of some rational terms, right? You have a polynomial in the numerator, you have a polynomial in the denominator. So all ordinary differential equation systems, all systems which can be represented using ODEs, ordinary differential equations, could be written in this form where there is a numerator polynomial divided by denominator polynomial. So this is what we refer to as the rational Laplace transform. So which is very useful for us to solve circuit analysis problems in RLC circuits. So if the Laplace transform is rational, then we can define something called as poles and zeros of this Laplace transform. So what is basically poles? Poles are nothing but the roots of the denominator polynomial, and zeros are nothing but the roots of the numerator polynomial. Why are they called poles and zeros? So let us say the numerator has some roots. We can factorize this polynomial into, let us say, s minus beta 1 into s minus beta 2 up until s minus beta m. Okay. So basically what have we done here? So we have took an mth degree polynomial and we have factorized that. So it has m roots, beta 1 to beta m. So if s takes the value beta 1, let us say, then you evaluate this polynomial at beta 1, what happens? It's after all the root. So if you evaluate the polynomial in its root, its value will be 0, right? So this value at a particular beta will be 0. So that is why this is called zeros. So any roots of the numerator polynomial are called the zeros of the Laplace transform. Now similarly, you can factorize the denominator polynomial. So let us say it is s minus some alpha 1 to s minus alpha 2 up until s minus alpha n. It has n roots because it is an nth degree polynomial. So if you evaluate at some alpha I, of course this polynomial is going to evaluate to 0. The polynomial is evaluating to 0, which means in this ratio we will have some n of s divided by 0 form, which means this will go to infinity. Okay. So at this particular point, at the roots of the denominator polynomial, the Laplace transform is going to infinity. So it's just rising up like this, and hence the term pole. Okay. Looks like in the graph it looks like a pole, so it's called a pole. So how many poles would exist for such a Laplace transform? Obviously it has capital N roots, which means at all those points it will become infinity. So the number of poles of a Laplace transform is equal to the degree of this denominator polynomial. And what if there are repeated poles or repeated roots? Then we say that a particular root, if it repeats, then the order of that root or the order of that polynomial is equal to the number of repetitions. So if it repeats twice, then we say that it is a second order pole. If it repeats 3 times, then we say it's a third order pole. If it repeats only once, it's a first order pole, or we say it's just a pole. Okay. Similarly, the order of 0 is the number of times the root gets repeated for the numerator. So for this example, what are the zeros and what are the poles? In this it has no zeros, so it has only one pole, and that pole is at s is equal to minus a. So if we draw the ROC, so you just say there exists a pole at minus a. The representation for a pole is by drawing a cross in the ROC. So at point s is equal to minus a, this term or this Laplace transform goes to infinity. So we know anyway that the ROC for this expression is a right-sided ROC. Okay. So what if there was a 0? So let us say if the Laplace transform looked like this, then there exists a 0 also here. What is a 0? At s is equal to 0, there is a 0. How do we represent that? In the ROC, we will draw a circle. So around the point of 0, we will draw a circle, and then we say that there is a 0 at that point. If somebody gives you an ROC plot with the poles and zeros plotted, and then they also give you a constant factor, then you can completely characterize a Laplace transform. So what is x of s? So you can write x of s as some constant times s minus alpha I, where I runs from 1 to m, divided by I 1 to n s minus alpha I. So in order to know this Laplace transform, we need to know this alpha values, this beta values, and this a. That's all. So if somebody gives you those numbers, then you completely know what is a Laplace transform. So all of this can be obtained in the ROC except for this constant a. So if somebody gives you an ROC which looks like this, that we have here. So from this, can you write the Laplace transform expression? Yes, we can write the Laplace transform expression. So from this, we can say that the Laplace transform expression is nothing but x of s. It has 1 0 at the point 1, which means the numerator has a polynomial whose root is at 1. So we s minus 1 divided by the denominator has roots at minus 2 and minus 1. So you have s plus 1 into s plus 2. So just by looking at the pole 0 plot, so this is what we refer to as the pole 0 plot, we can directly say what the Laplace transform expression is going to be. Of course, there could be a constant to this. So if somebody gives you the ROC with the pole 0 plot and this constant a, then you know everything about the system. There is nothing more left to know about the system. And remember, all this makes sense only for rational Laplace transform. So pole 0 plot makes sense only for rational Laplace transform. So why do we even study this Laplace transform? We saw that we study Laplace transform because Fourier transforms may not exist for certain cases. So we study Laplace transform. And then we saw that Laplace transform is fully defined only when ROC is also given to you. Now we are seeing a different thing, the pole 0 plot. And the pole 0 plot is specific only to rational. And we are focused on this because we saw that the circuits could be modeled using ordinary differential equations. And ordinary differential equations could be eventually expressed as these rational forms when we compute the transforms. And hence we focus on rational Laplace transform. And rational Laplace transform can be fully defined by the pole 0 plot. So this is a very simplified way of representing pictorially the Laplace transform.